Very good morning, one and all. I extend a very warm welcome to all the participants for this fifth day of our faculty development program. Let us proceed with today's program. I call upon Akshata Madam to take over.
Yes, sir. A very good morning, one and all present here. I am Akshata S., Assistant Professor of Commerce, GFGC Gauri Bidnuru. Heartily welcome you all for the fifth day, 1 week virtual national level faculty development program on research methodology in social sciences. I request all the participants to mute yourself, turn off your videos during the session. The queries pertaining to the technical session to be put in the chat box only, which should be put in the chat box only, and which will be done at the end of the session. Feedback link will be provided at the end of the session and will be posted in the chat box as well as in YouTube live stream, YouTube live chat. And then it will not be again put in the WhatsApp group. Okay, please make sure that you're giving the feedback using the given link at the end of the session. If any queries regarding the program or any concerns or issues regarding the program, please let us know via WhatsApp group. Okay, with this, I'll just now call upon Srimati Parvatamma, Assistant Professor of Commerce, GFGC Gauri Bidnuru, to invite welcome the gathering. Over to you, Parvatamma Madam. Parvatamma Madam. Parvatamma Madam, are you there? All right. Yeah. Ma'am, unmute yourself, ma'am.
Good morning to all the participants. It's my privilege to welcome you to all for the fifth day faculty development program on research methodology in social science organized by Department of Commerce and Management in association with IQAC and Academic Research Group Polar. I would like to welcome our beloved principal, Professor M. Shivanna, who inspiring for organizing and this program. I heartily welcome to you, sir. I wish to extend warm welcome to today's guest and resource person, Professor L.T. Balaji, Associate Professor from Government First Grade College, Vemgal. I heartily welcome to you, sir. I also extend my heartily welcome to Professor Gangadharaya, Assistant Professor of History Department and HOD of History Department, IQAC Coordinator. I heartily welcome to you, sir. I would like to extend my heartily welcome to Dr. Madhusudan Reddy, HOD of Commerce Department, Dr. Zabiullah sir, HOD of Management and convener of this program. Welcome to you, sir. I would like to extend warm welcome to all teaching and administrative staff to this program. Welcome to you all, sir. Last but not least, I invite all the participants for the fifth day faculty development program organized by GFGC Gauri Bidnuru. On behalf of Government First Grade College, IQAC and Academic Research Group, I welcome all of you. I would also thank to Akshata ma'am for giving this opportunity to me. Thank you very much, Akshata ma'am. Over to you, ma'am.
Thank you, ma'am. Welcome to you. Now, I'd like to call upon Sri Manjunath BN, today's rapporteur, to introduce our resource person, Professor Balaji, Assistant Professor of Commerce and Management, GFGC Vemgal. Over to you, Manjunath, sir.
Good morning, madam.
So can you just higher your pitch? It's a little bit voice
Good
too.
morning, Akshata madam.
Good morning.
Am I audible? Hello, Akshata madam.
Matadi
Am I
sir.
audible?
You're audible. You're audible. Matadi sir.
A very good morning to all the dignitaries and participants, respected principal, coordinators, teaching staff and non-teaching staff of Government First Aid College, Gauri Binnur. I would like to introduce today's dynamic resource person, Lieutenant Balaji A. He is working as an associate professor of commerce and management and also associated NCC officer in the rank of lieutenant in Government First Aid College, Vemangal, Kolar district, Karnataka. He has cleared UGC NET exam 4 times. Really, it is very good achievement and remarkable also, along with JRF. Also KACT. He is also a sports person. Sir also completed a rescue course in National Defense College, Nagpur. Sir also presented many papers at national and international conferences and seminars. Also won best paper awards also. He is carrying research currently in high frequency trading in stocks and commodity markets. Sir holds master degree in commerce from Bangalore University, besides an MBA in e-business. His area of specialization is finance and e-business, psychometrics and econometrics. Today I am very grateful to introduce an eminent professor, Lieutenant Balaji sir. I am very grateful for this opportunity. Thank you very much, one and all. Over to Akshata madam.
Thank you, sir, for a great introduction. Now, over to you, Balaji, sir.
Madam, can you hear my voice, madam?
Yes, sir. Yes, sir. You're audible.
Okay.
Please turn on your video, sir.
I still think my screen is not being visible, madam.
It's visible, sir. It's visible. Your screen is visible, sir.
Okay, thank you.
Ah.
Okay, first and foremost, good morning to all the participants to 5 days FDP on research methodology in social sciences. I'm first and foremost grateful to the staff of GFGC Gauri Binnur for providing me an opportunity to present what I know regarding inferential statistics in research methodology. I thank the principal of GFGC Gauri Binnur along with the IQAC team, the MC Akshata madam, and the rapporteur Manjunath sir. Okay, and I also thank the most important person who was instrumental for providing me with a lot of opportunities to present regarding research methodology. It is none other than Murlidhar sir. Not only me, he is a person who recognizes a lot of youngsters and give them opportunities, yeah, and give them a place to grow under his wide umbrella. Okay, so over to this, the topic, and I also, last but not the least, I also like to thank you, my staff at GFGC Vemangal, my principal, who all gave me permission to cancel all the classes and attend this session here. Okay, so first and foremost, the topic which they have allotted to me was parametric and non-parametric methods. Okay, but before going to parametric and non-parametric methods, it becomes imperative for people in order to know very basics of statistics to be used in research methodology. And everything starts, and your research starts from your day-to-day activities. Okay, so the seeds of research is there in and around you. Okay, so first and foremost, let me go to the first slide. So can the rapporteur or the MC, could anybody tell what is happening here? Ashita madam, can you tell what is put in this picture?
Sir, we are flipping the coin, sir. Either we get a tail or a head.
Okay, thank you, madam.
Sir.
So basically, we are tossing a coin. Okay, so let us see, when you're tossing a coin, it is an event. Okay, it is an action, and because of this, there is two events can occur. Either you can get a head or a tail. Okay, so what is this?
Dice.
Okay, it's a dice. When you throw a dice, a single dice, let us keep your throwing a single dice, there is a possibility that you can get either 6 outcomes. What are the 6 outcomes? You can either get 1, or you can get 2, 3, 4, 5, or 6. Okay, so what is common between an coin toss and then die roll? Okay, so first and foremost, there is an event happening in coin toss. You'll get an outcome either head or a tail. So there is 2 outcomes and 1 event. Okay, so the 2 outcomes are head by tail. When you divide it by 2, you get 1 by 2. The answer is 0.5, and when you plot in a graph, you get head is 0.5 and tails is 0.5. Okay, and observe one thing clearly. This is a probability distribution. If you add these two, 0.5 plus 0.5, it sums up to 1. It sums up to 1. Similarly, when you do a die roll, okay, so you see what are the outcomes can happen? 1, 2, 3, 4, 5, 6. And any one only can occur. So the total possible outcomes are 6. Out of that, 1 can occur. So when you get it in a fraction, you get to 0.1666 is recurring. When you plot it in a graph, you can see 0.161. The probability of it occurring is 0.166. Probability of 2 occurring is 0.166. Probability of 3 occurring is 0.166. 4 is 0.166. 5 is 0.166. And 6 is 0.166. Okay, so again, note one thing. If you add all these 0.16, 0.166, 0.16, if you add it 6 times, again the total you're going to get is 1. Okay, so pretty simple, right? We have learned, we all know this one. Okay, so let us go a little bit to an advanced slide. Okay, this is a bus stop near my MCOM college. Okay, so long time photo, I tried to put it here once. Can somebody tell me what's happening here?
So few are waiting for the bus, and
Yes.
few are chatting with friends. You are just simply sitting. There are like certain
So
different
few are
aspects.
waiting for the bus. We'll take only that concept. Of course, Korea students, they like to chat, but this few are, let us think few people are waiting for the bus. Okay, so let us assume that a bus was supposed to arrive at a particular stop at 11:30 a.m. Okay, however, the record indicates that in near Maharani College on time the bus will never come. Okay, so what happens? The bus arrives anywhere between 11:25 to 11:35. So let us see the likelihood of the bus arrival in the next minute. Okay. So what are the different times the bus can come? Bus can come from 11:25 to 11:35. So the bus can come at 11:26, 11:27, 11:28, 11:29, 11:30, 11:31, 11:32, 11:33, 11:34, and 11:35. So basically, how much is there are 10 possible minutes where the bus can come. When you try to plot this in a graph, you can see a 1 divided by 10 outcomes. Bus coming is 1 event and the outcomes can be 10. So the probability of any bus coming at any one particular minute is 0.1. And again, you add all this 0.1, 0.1, 0.1, you add it 10 times, again you get a total of 1. So any kind of distribution, the total of all the possible outcomes will always be 1. This is a very key point to remember. Okay, so this forms the basics of your entire understanding your parametric or non-parametric studies. Understand one thing here. If there are 2 events, the height of the event is larger. When there is 6 events, the height becomes a little bit lesser. When there are 10 events, the height becomes much more lesser. So when the number of events become more and more and more, the height of a particular event happening becomes lesser, lesser, and lesser. Okay, so that the above 3 examples are an example of the above 3 case studies which I gave you can be taken as an example for uniform discrete probability. You can discretely identify how much times this particular event occur. What is the probability that this particular event can occur? Okay, so based on that, let us see the anatomy of an uniform discrete probability. The function of an event occurring is 1 by n outcomes, and the total area is always equals to 1. When the number of outcome increases, the height will decrease. The height will decrease. So these are a little bit identifiable very clearly. But what in a real world, we researchers are dealing with data such as temperature, distance, income, mass that can be measured to several decimal points. For example, weight. Weight, you can take even atomic weights also. You can give an accurate weight of an item until 100 decimals also. So what will happen is, if you ask what is the possibility that a particular an object will be of a particular weight, okay, so now the number of possibilities will start moving towards infinity. The number of outcomes will start moving towards infinity. So therefore the probability will become 1 by infinity. The probability will become 1 by infinity. Just look at here. This is 1 by 10. This is 1 by 6. This is 1 by 2. When you take, for example, what will be the weight of a object X? Okay, I can. What would be the weight of an object X? I can tell the object X weight can be from 10 kg 0.37892 to 10 kg 0.4789678. So you can just imagine as you increase decimals, the outcome will start moving towards infinity. Okay, when you want more and more precision, the outcome will start moving towards infinity. Therefore, the probability becomes 1 by infinity. Okay, but 1 by infinity is equals to 0. Okay, many people tell it is undefined, but for a simple understanding, let us keep it as 1 by infinity is equals to 0. Now, what will happen? I told you, when this denominator becomes bigger and bigger and bigger, the height of the bars will become smaller and smaller and smaller. Okay, so this is an example of uniform continuous probability. Okay, so from discrete we came to continuous probability. So let us see. For example, let us take one simple example. Okay. Let us think you are working in an atomic research center and you wanted to measure a weight of a particular item. Okay, the particular item's weight you want it to be between x1 and x2 points. You want it to be between x1 and x2 points. Okay, in that atomic center, when you do an experiment, a particular item will have a mass between x1 to x2, But in order for the project to be successful, you want the weight to occur between A and B. So what is the probability that you would get the requisite weight? So what we can do is we can take the area from A to B and divide it by the area from your x1 to x2. So basically the formula will become B minus A divided by x2 minus x1. Okay, I know now it's getting a little bit technical, but nevertheless, you got to understand these things. And the area from x1 to x2, it will always remain 1. I'll try to explain this with a simple, the previous example. Okay. Okay. So a bus can occur from 11:26 to 11:35. What is the probability that the bus will occur from 11:29 to 11:30? Okay, so let us take this. Okay, so let us see what is the probability that it will occur from 11:26 to 11:35. What is the total probability? The total probability here, 11:35 to 11:26, the total probability can occur as 10. The total probability here is 10. Now I asked, what is the probability that it will occur from a bus will come from 11:29 to 11:30. So there are 2 minutes possible. So I will write it here as 2. So the probability the bus will occur is 1/5. Okay, the probability is the bus will occur is what? It is 1/5. Okay, so now let us try to put this in a format which the formula which I gave you all. Okay, the formula which I gave you all was, okay, here you can see x2 minus x1 divided by b minus a. So what you can do is you can minus this one from this and minus this probability from this, you'll be getting the same value. Okay, so this is an example of uniform continuous distribution. Now from uniform continuous distribution, now let's start slowly moving towards normal distribution. Okay, normal events can be anything that's natural, like human height, human weight, temperature, blood pressure, etc., or man-made items like machine products, financial data, etc. Okay, now what happens is researchers have observed through the ages that when you take a lot of normal data, measure it, and when you measure it, when you try to plot it, most of the data try to cling towards the centermost point, or try to cling towards the center. Okay, in our statistics, you might have been heard as measures of central tendency, mean, median, mode, all those kind of things. So similarly, what happens? Natural items or man-made items, okay, which is not being controlled by humans. Okay, the output is not being controlled by humans in order to manipulate data as such. Anything which occurs randomly, what happens is all the output tries to cling towards the center, and towards the tails, what happens is there become less and less observations. Okay, so let us take one simple example. Let us think that, okay, just a minute. So let us think we are talking about human height. But there are people who are also 2 feet tall. There are also the people who are 9 feet tall. Okay, but what happens is in India, most number of people are in and around the height of 5 feet 6 inches. There are also people in 2 feet, but there are less number of people you can find there. So you can tell there are less observations at this extreme, and very less people who are there at 9 feet tall. So again, there are less observations at this extreme. Most of the data are being in and around for 5.6 feet. This is called as normal distribution. Okay, so let us see. So what happens? The average of the observations in your theoretical population, if you take it as 0, and from there, the first deviation, positive and negative, you'll again find 68% of the observations. And from the second deviation, both negative and positive, you can find 95% of the observation. And between the negative third standard deviation and the positive standard deviation, you find 99.7% of the observation. Okay, so this is a basic knowledge which you people have to know. Okay, so whenever you're trying to test the data, if you got to find if your data is trying to get fitted in a distribution in the normal distribution, follows a pattern of normal distribution, then what happens? You will be able to take a small sample and you'll be able to infer how the entire population will be using the crux and the explanations and the body of literature available that are built around this normal distribution tables. Okay, so regarding this, I like to tell you, based on this, the concept of Z scores are available. Okay, so let us understand a little bit about normal distribution. Your normal distribution will be usually a bell-shaped curve. Okay, and at the central tendency point or at the central point, there will be a huge concentration of observations, and as you move towards the more and more deviations, either positive or negative, the observations become less. And you got to one thing observe, that this bell-shaped curve will never touch this x-axis. Because it never touches this x-axis, it is called as asymptotic curve. It is called as asymptotic curve. Okay, so even if people are doing sim modeling, you will know there are different kinds of methods to do sim in your covariance based sim models, asymptotic distribution free models, maximum likelihood methods, GLS methods, all those kind of things. So in order to understand at that level, you got to understand these concepts clearly. Okay, so before going further, let us analyze this bell-shaped curve a little bit in detail. Okay, so just a minute. Okay, so I'm having a bell-shaped curve. Okay, so when I'm having a bell-shaped curve, let me take okay, blue color. Okay, so somebody tell me what would be the area under this curve. Okay, I can see in your chat boxes. Okay, yes, correct. The area under this curve will be equals to 1. The area under this curve will always be equal to 1. Any distribution, the area under the total area of the distribution will be 1. And let us check this. What would be the area exactly half of this distribution? Okay, what would be the area of exactly half of this distribution? Okay, so just a minute. Okay, little bit it spilled over the curve, but within the curve, what would be the area? The area under this curve, if the total is 1, half of it will be 0.5. Half of it will be 0.5. Okay, the half of this will be exactly 0.5. Okay, so this one you got to remember. So let us see what would be the area from -1 to 1, -2 to 2, -3 to 3. Okay, what would be the area from -1 to 1, -2 to 2, and -3 to 3? Okay, so let us see, let us check this one both in your table also, and let us check again in your Excel also. So now let us see the new area. Okay, until 1, what is the area? Okay, so until 1, what is the area? So let us go to your table. You can see exactly under 1, the area is 0.8413. Until 2, the area is 0.9772. Until 3, the area is 0.9987. Okay, so this is what has been given in your table. Okay, so let us write one -3, -2, -1, 0, 1, 2, and 3. What I'll do, I'll press equals to. I'll select normal standard distribution. You can see for 0, it is 0.5. Okay, I told you exactly half. 0 is there exactly at half, so it will come 0.5. For 1 is 0.841345. And similarly, you can see here 1 0.8413. For 2 is 0.977725. 9772. So Excel is giving us a little bit more accurate values. So now what we require, we have to find out is what is the area between -1 to 1. So what we'll do is from 1, we'll subtract -1 value. Okay, so -1 to, sorry, -1 to +1, -2 to +2, -3 to +3. So what I'll do, I'll go equals to this one minus this one. I got 68.2689. I got here 68.3. Okay, so same value. Your -2 to P2, let us see here, equals to 0.97725 minus this, you get 9545. I write here 95.4. Now again equals to 0.99865 minus this one 99.73. You can see here, I got here again 99.7 itself. Okay, so this is the basically the Z score you got to remember. Now, because you understand, I assume that you understood the Z score properly. We'll move to the how to use this in research. Okay, so how to use this in research? When you do quantitative research. Okay, so basically, I think in first day you have been introduced with what do you mean by qualitative and quantitative research, but basically we are now dealing with quantitative research. In quantitative research, we are mostly interested with large population. The average income of salaried people in Bangalore, it will run in lakhs. The total consumption of middle income family in Bangalore, again the number of observations can run even in to 1 crore also. Okay, but due to the time limit and cost, we are not able to use data to what we'll do is we use a small data to represent a larger population. Now I'll tell you, when you're doing quantitative research, how you should do the sampling. Okay, the first thing, how to do a research, every person has to learn from his mother. Okay, how? I'll tell you. You think in your home, your mother is cooking a rice in a pot. How she will determine whether the rice has been cooked or not? First, what she'll do, she'll take and stove, she will mix the rice and randomly take one, determine whether that rice has been cooked or not. If that random rice is cooked, she is going to decide that the entire rice is cooked, and always she is right. The same thing we are going to do here also. If you want to check the average income of salaried people in Bangalore, what we are going to do? Randomly, we are going to select people, salaried people in Bangalore. Randomly, I'm again telling you, this should be random. Okay. I think Divya madam has explained about this sampling methods and all. I'll not go much into it, but I'm telling you, for all this distributions, methodologies, t-test, z-test, chi-square, all these to work, you are going to use random samples. Randomly, I'm going to select from your theoretical population the observations, and you're going to check what is the random salary of people, and then determine what would be the average salary of people in Bangalore. But what happens, can you randomly select only one person, take a note of his salary and determine what would be the salary for the entire Bangalore? No. 10? No. 30? No. 40, no. 1,000, okay. 10,000, okay. So what you can see here is, as the number of sample size increases, your confidence will increase. That's what you're going to study next, okay? And the number of sample size decreases, there's a greater risk of error. And one more thing is, if you are able to know the details of the populations, mean, variance, it will be much more easier for you to do the calculation. If you do not know, we are running into an additional risk also. Usually what happens is, when you take a large sample size, you'll capture the diversity, natural variation, everything. And again, how large it should be. Sampling also adheres to, most of them I think are from a social science background. So you all know something called as economy of scale. Okay. After a particular, then you know about economy of scale, you know, the diminishing returns theories, all those things. So again, your sampling also adheres to these basic economic principles. After a certain point, no matter how much you increase the sample, there will be no additional yield. So that's why you can hear somewhere people telling this magic numbers like 283, 600. We'll see how we are come to those numbers. After those particular point, if you add any extra observations also, there will be no visible benefit to your problem interpretation. Okay, then now because you understood Z distribution, now let us come to T distribution. What will happen when your sample size is less than 30, or you do not know the population standard deviation or the population's other parameters? During those times, what you're going to do is you're going to use T distribution instead of Z distribution. Okay, so T distribution allows us to use even a small samples like sample size less than 30 also. But when we use T distribution, there is a possibility of margin of error. Okay, and the sample size takes into account n-1 degree of freedom. Okay, so what will happen is, when your sample size decreases, the bell-shaped curve gets squished in between and the tails become fatter. Okay, so let us see how that how that thing happens. In order to explain your T distribution curve better, I can tell you an example of Burger King bun. If they'll give you a very big bun which will not fit into your mouth, when you try to bite that bun, what will happen? The center will become pressed and the sides will get opened and the sauce will be on your hand. Similarly, what's happening from a full bun, when you try to take out a little, the center becomes small, and you think this is a bun, you take a little, what will happen is the center becomes small and the tails become fatter. Okay, the tails become fatter. When you take a thing, what will happen? The curve will become like this. Okay, the center will become smaller, the tails will become fatter. Much more you take, the curve will become like this. Sorry. The curve will become, the center will become much more fatter and the center will become much more smaller and tail will become much more fatter. So what happens as the sample size decreases and decreases and decreases, the average will become smaller, the data concentrating towards the average will become smaller, and the data getting concentrated at the deviations become more. Okay, so how to decide whether you're going to go for a T or a Z? If the parameters of the population can be known, go for Z. If it's not able to be known, go for T. Okay, so there is one small stock written example. When I give it up, when I share this PPT with you all, I think you people can work out this and try it. I can share even the answers also. Now let us move to the crux of today's meeting, that is inferential statistics. Okay, so what do you mean by inferential statistics? Inferential statistics means making conclusions on the data available about something larger. Making statistics, inferential statistics means making conclusion based on the data available about something larger. Okay, so let us see. Pavers Limited is a company specializing in residential road surfacing. Okay, so what they do is, in foreign countries and all, they'll try to put a rubber and asphalt mixed roads, so that what happens is there will be less friction, and the sounds also, there will be less wear and tear of their cars. Okay, so one particular company by the name Pavers Limited is a company specializing in residential road surfacing. Many of its clients seek out a specialized product, low noise pavement. Okay, recycled rubber can be added to asphalt mixtures to reduce the road noise, which appeals to the environmentally conscious clients. Okay, so when they mix rubber to the asphalt mixture, the road noise will decrease. However, the viscosity means how stretchable is a particular material is called as viscosity. For example, when you're putting road, if it is very stretchy, vehicles will start skidding. If it is very hard, there will be huge wear and tear. So there should be a correct stretchability. We call it as viscosity. Should be maintained within very tight limits. Otherwise, it will become too thick or too watery. The goal of the viscosity is 3200 with a deviation of 150. During the manufacture of each batch of asphalt, the quality control specialists take 15 samples of the material to test the viscosity. Okay, note this point. They're taking 15 samples. This also ensures the batch has uniform viscosity. Okay, so let us see. This is a real life data from a real company. We will try to use it. I already calculated it, but there will be no issues for you all. What happens? They take a specimen. They told 15 samples. Specimen 1 is 3193, 2 is 3124, 3 is 3153, 4th is 3145, 5th is 3093. There are some things, many things are below 3200, some things are above 3200. You can see they have told it should be 3200 with a standard deviation of 150. So the sample mean is 3210.73 and the sample standard deviation is 117.61. You can put it in Excel or you can manually calculate. You will be getting this value. Okay, so you are getting a sample mean of 3210 and a sample standard deviation of 107.61. So with this data in mind, let us decide whether this particular batch passes a test. Let us decide this particular batch passes the test. Okay, so this introduces us to the concept of point estimators. Okay, so let us see what you mean by point estimators. Okay, point estimators are never perfect. They always have an error of component. This is called as marginal error. Technically, we call it as plus or minus percentage of the confidence interval. Okay, so what we are doing here basically is, out of a particular batch, we take one sample. Again, from the next batch, you take another sample. From a third batch, you take another sample. Fourth batch, you take another sample. So you take a lot of samples. For all the samples, in each sample, how many times you take the specimen? You take 15 times. So remember, this is batch 1. You're taking 15 specimens and the sample mean of it calculated by like this. You got 3210. Again, in batch 2, you take it in it and you got a sample mean of 3150. Third is 3345. Fourth is 3190. Fifth is 3217. Sixth is 3310. Fourth is 3100. Then eighth is 3413. Ninth is 3023.59. Now what we'll do is we will make an 100 group range. We'll convert this data into an class interval. So 2950 to 3049, 3350 to 3449, increasing at levels of 100. So between 2950 and 3049, you can see there is one variable, 3049. Yeah, the ninth one. Between 3050 and 3049, you can see one observation. So like that, if you start plotting, you can see 11421. Okay, you can see most of them are getting concentrated in the middle. If you plot it in a graph, can you all see that again this forms a bell-shaped curve? Excuse my drawing, because my drawing, I think it's not perfectly bell-shaped, but you can see. Okay, it is almost bell-shaped. Okay, it is almost bell-shaped. So we can tell that this sampling distribution through visual observations, this sampling distribution follows your normal distribution. Okay, so okay, so based on this, can we tell whether this particular samples, that the previous sample is a pass or not, whether you can approve that batch or not? Now let us see how to determine those things. Okay, before going further, you got to understand that the standard error of the mean is same for all the sample means. The standard error is the standard deviation of the sampling population. Okay, so let us come to the concept of confidence interval. So what happens? You think from a particular batch, you take 20 samples. You take how many samples? You take 20 samples, and imagine that you are taking a 95% confidence. You are taking 95% confidence. Okay, so what do you mean by 95% confidence? That means you take the populations, you take the population's average, you take the mean of the population, and you extend the line below. And then what you try to do is you take the various samples, sample 1, sample 2, sample 3, sample 4, 5, 6, like that, 20. 19 times out of 20, you can see 20 into 95%, you'll get 19. 19 out of 20 times, what will happen is, if you're 95% confident, the population mean will form the part of the samples distribution. Okay, that means this is a sample distribution, this is a sample mean, this is a total sample distribution. You can see this population mean touches this particular sample mean, this touches this particular mean, this touches this particular mean. Fifth one is great because the population mean and the sample mean are same. Like that, you keep on doing. Only the 11th one is not touching your population mean. That means in this particular distribution, the population mean is not a part of this particular distribution. So 95% of the time, your batch will be a success. Okay, so how to interpret this? You got to remember that the sample is random, not the theoretical population. So the randomness lies in the sample and not the population mean. That means the randomness lies in this particular samples, not in this theoretical population. It is the probability of obtaining and representative sample. That means the probability that you will get a sample which represents the population mean is what you're going to study under confidence interval. Okay, so it is a probability of obtaining a representative samples. The proportion of sample size n, which is our estimate, the sample mean is within a certain distance plus or minus of the true mean or not. That means from here, from the sample mean plus some distance, you have the population mean. From here, minus some distance, you have the population mean. So it happens in that particular way. Okay, and the confidence interval also depends upon the sample size, confidence level, and the standard deviation of the population. Okay, so this is how we are going to interpret. Now, what happens when we do not know the standard deviation of the theoretical population? Okay, that time what we do is we got to use student t distribution instead of using the standard deviation of the theoretical population. Use a standard deviation of your sample itself to calculate, to arrive to conclusions. Okay, I told you, you see here, this is your degree of freedom. The black color line is your z-score line. Your black color line is this is your normal distribution. Okay, so what happens as the degree of freedom decreases? You can see degree of freedom decreasing from infinity. It does decrease to 6 to what happens? This normal distribution curve, the center point becomes lesser and the tails become fatter. This becomes lesser and tail becomes fatter. This is what is called as t distribution. So this is the error which you are going to pay for using t distribution. Okay. So you can see I have put in a t distribution table. In a t distribution table, let us take your test. In the test, you can see that in the Z distribution, 95% confidence level, it is 1.96. The value is how much? It is 1.96. You can see as the degree of freedom increases from 1 to 2. Observe this particular level. From 12, it becomes 4, 3, 2, 2, 2, 2, 2, 2, 2, 1. After 600, the value of a t-test and a Z table becomes equal. Okay, so what happens is as you increase your samples, your t distribution will merge with your Z distribution table. Okay, so basically, if some people are telling they use t-test, they're basically using the primary test which we have just discussed, normal distribution test. Okay, so as told earlier, your point estimator as a component of margin of error. So every point estimate, it has a sample mean and then margin of error. Sample mean, it is represented as x bar, and the margin of error is nothing but the standard deviation. It is nothing but the z into deviation divided by root of n. So therefore, if you just take this particular part, sampling mean, this is sampling mean, and this is margin of error. Margin of error is equals to z into sigma divided by root of n. So in order to decide so if you want to know how much is the sample size I require, just do a simple transposition. N becomes z sigma by e into square. You can do a simple transposition, you can get. So if you know how much is the margin of error you're ready to accept with the sigma level and the z score, you'll be able to determine the number of samples you need to you require to calculate for your research. Okay. So now let us come and we'll try to decide how to make the hypothesis. Okay. So I'm not going much more technical. I'll just stick to the basics. Already your hypothesis formulation and all has been explained. And yesterday, even Usha Madam also did a wonderful work of telling what are different kind of hypotheses possible for both parametric and non-parametric studies also. Okay, so let us see. I'll just try to catch a basics, because without this we will not be able to proceed a bit further. Okay, so hypothesis is a proposed explanation made on the basis of limited evidence as a starting point for further investigation. Okay, null hypothesis are usually statements which are accepted as true. Okay, so what happens? It represents status quo. It contains symbols like equal to, greater than, equal to, lesser than, equal to. The opposite of this is alternate hypothesis. It contains not equal to, lesser than, greater than symbols. Okay, so basically let us see here. We'll try quickly to go up with your how to frame the hypothesis formulation. You got to remember one thing. Most of the researchers, what they do is they on themselves, they start creating a questionnaire, or they develop the scale on themselves. That cannot be done. Okay, usually what you got to do is you got to, if you're doing exploratory factor analysis, it's okay, exploratory study, it's okay, but most of the time what happens is we try to test some established theories. Okay, so what happens is we got to study a theory, and based on that theory, somebody would develop scales for the various variables. You got to take those scales and you got to test, prepare your questionnaire. But in case you're going to go for exploratory, what you got to do is you got to use mathematical hypothesis. You got to use mathematical hypothesis. I'll tell you how to do that one in a simple. A bottled water manufacturer state on a product state on the product label that each bottle contains 500 ml of water. You work for a government agency that protects the customer by testing the product's value. Okay, a sample of 50 bottles is tested. Okay, a sample of 50 bottles is tested. So let us see how you are going to write the hypothesis for these things. Okay, so let us try to see how we are going to write the hypothesis. Now, first and foremost, you got to know if a bottle contains more than 500 ml, the company will be at a loss. If they're filling less water, customers will oppose. The company will lose the customers. So exactly what happens is the water should be exactly equal to 500 ml. So what you're going to do is, in this first one, the null hypothesis is the mu should be equal to 500 ml or the mean, and the alternate hypothesis is the mu is not equal to 500 ml. Okay, so this is one particular hypothesis. This you can see there is no greater than or lesser than sign here. So because there is no greater than or lesser than sign, this is called as a two-tailed test. You got to do two-tailed t-test. Okay. Now next one. According to US Department of Agriculture in 2006, the average farm size in the state of Texas is 2.3 square kilometer. Since a decade-long trend, there has been a farm size to increase due to large agribusiness. A business analyst wishes to test if in the current year the farm is larger than it was in 2006. So what happens? I told you null hypothesis is a statement of no difference. So I'll write here the second one's null hypothesis, H0. Here you want what is stated, whether this trend has been changed or not. He wants to see whether the trend has been changed or Not. So what you're going to do is H0 wherein mu is greater than or mu is lesser than or equal to 74961. That means you're trying to find whether it has remained in the lesser than or equal to 2.3 square kilometer. That means you're trying to find whether the farm size has been remained the same or if it has even decreased also. Now what happens? The alternate hypothesis becomes mu is greater than 2.3 square kilometer. Okay, there has been an increase in the size. So alternate hypothesis points to increase in the size, that becomes more than 2.3 square kilometer. Now you can see this sign points towards right side. So this in the alternate hypothesis, if this sign points to the right side, so it becomes a right-tailed test. Okay, so now let us see the third one. During 2013-14 IPL season, Royal Challengers Bangalore matches had on average attendance of 74,961. A club marketing analyst would like to see whether the attendance is decreased or not. So he wants to see whether it is decreased. So alternate, you are going to try to put it as H0 M. It is greater than or equal to 74,961, and your H1 becomes mu lesser than 74,961. You can see here this arrow is pointing towards left, so it is a left tail test. Okay. Okay. Similarly, we have other things also based on Likert scale, all those kind of things also. We can actually can do the sum manually also. I can tell you how to do your entire t-test and z-test. One thing got to remember, many people wants to, when they start research, they immediately want to try to jump into SPSS and do things. But SPSS is a GUI program. Only if you know, it will give you some values. Okay, so you got to know the basics of things. You got to know how to do it manually. You got to know how to do it using Excel. Then you go, then you will automatically, nobody needs to teach you SPSS. You will be automatically able to deduce on yourself how to do SPSS. And one more benefit is, if you know how to do it manually, you can do the entire all the sums directly in R. R is the most powerful research tool. For example, in researchers, if you're going to do econometric analysis, you're going to use E-views. If you're doing a little bit psychometric analysis, all those kind of things, your people go for SPSS. But if you know R, you can do everything there. Okay, and in order to do that, you got to know the basics of statistics. Okay, so basically, what you studied till now are parametric methods. In this parametric method, the observations must be independent, and the observations must be drawn from a normally distributed population or any kind of other distributions also. The population must have the same variations. The fourth point, I'll not go to explain it much because I'm running out of time. So I'll not be able to explain the fourth point. I'll just tell you the means of these normal and heteroscedastic or homoscedastic population must be linear combinations of people due to rows and columns. Okay, non-parametric. Now what happens? Suppose the sample which you are taking, it does not follow the bell-shaped curve. It is skewed. There comes the use of non-parametric studies. Okay, so what happens in non-parametric studies? Observations are independent. Variable should have an underlying continuity. I think Sairam sir in the second day has explained wonderfully regarding your different kind of variables, your nominal, ordinal, then your interval and ratio. Nominal, there is no distance, no origin. There are different kind of postulates in your measurement. Okay, ratios can be measured by postulates of measurements. Okay, we call it as postulates of measurements. You're going to see whether there is a concept of zero, then whether there is order, and whether there is distance. So basically you have nominal, ordinal, then you have interval, then you have ratio. If you have your data does not have any zero, order, or distance, then it is called as nominal. If it has only order but no zero and distance, it is called as ordinal. So we can tell ordinal, nominal is not continuous, but ordinal is continuous. So in non-parametric, you can do even ordinal data also can be used for doing your non-parametric methods. Okay, this is also called as categorical variables. Okay, just for information. In interval, there is a concept of order and distance like temperature, but there is no zero. In ratio, there is like height, weight, etc. There's all the three: zero, order, and distance. We call this one as postulates of measurements. Okay. So regarding this is your chi-square distribution, a non-parametric distribution. So quickly, I think I have another 5 minutes of time. I request for just 5 minutes extension of my session so that I'll be able to do justice to my presentation. Okay, so just I'll take another 10 minutes of your time, then I'll quickly wind up. Okay, what is your chi-square distribution? Okay, so you can see this chi-square distribution, you can see it looks like one side of the bell curve. I think people can see this, it has your one side of your bell curve. So what is happening is, let us see, let me try to draw your you take a distribution. You take a distribution with standard deviation. You take an observation called X. You take an observation called X, and this X is from a normal distribution. And what happens is, this X, you try to square it. You try to square it. Then this becomes a chi-square distribution of degree of freedom of 1. Next, what happens? You take another variable X and one more variable here 2. Okay. Now this what you do is you square this one also, you square this one also. You'll get a new variable. Now let us name this variable as Q1 and this variable as Q2. This Q2 is in sum of 2 observed variables from an normally distributed variable, but you're having 2 different observations. So this becomes a chi-square variable of degree of freedom 2. In similarly, if you're going to take 3, if you're going to go for degree of freedom, you're going to take 3 particular things. Now, why you're going to square all this? If your data is skewed positively or negatively, when you square it, all those things will get evaporated. So you can still test it here. Out of the 100 great discoveries of the last century, chi-square distribution has been considered as one. It is very, 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 very robust. You can use it for everything. Okay. And even if your data does not follow normal distribution, you can still use your chi-square distribution. Okay. Based on this chi-square distribution, there's a lot of non-parametric studies. Okay, so this is a chi-square distribution. Okay, so you got to understand there is at least one non-parametric test equivalent to parametric tests. These tests falls into several categories: test of differences between groups, test of differences between variables, and test of relationship between variables. Okay, so basically if you're going to compare two samples, in parametric you have t-test, in non-parametric you have Wald-Forfitts, Run's test, Mann-Whitney test, Kolmogorov, Shimogrov, two sample test. If you're going to do multiple analysis, what you can do is you can use in your parametric ANOVA or MANOVA. In non-parametric you use Cruxell-Wallis and median test. If you're going to compare two variables measured in a single variable, in parametric you do t-test for dependent samples, in non-parametric sign test and Wilcoxon test. In order to do all those tests and understand how these things values are used, you got to first know the basics of what I explained. Okay, if more than two variables are measured in the same sample, in parametric you use repeated measures ANOVA. In non-parametric you use Friedman analysis of variance and Cochrane Q. Okay, Cochrane has also given a formula for determining sample size. I think it is in 1975. You can check this paper in case you're going to give reference of how you got the one of the most frequent questions by people in research panelists. Where did you get this magic number of 600, 283? That time you can point to this particular person, Cochrane. Okay. Next one is two variables of interest are categorical. In parametric, you have correlation coefficient. In non-parametric, you have Spearman, Kendall tau, coefficient gamma, chi-square, phi coefficient, Fisher exact test, Kendall coefficient of concordance, etc. Okay, so basically I given a chart. You can determine in this. I just explained your one sample t-test, and I also explained your chi-square. Okay, I think chi-square test. Yeah, I just explained this one and this one. These two forms the basics for understanding all the other things. So here you have for what kind of situation, what kind of test to use, if you have for a ratio interval data based on your data and for your goal. Okay, RIN, you can see the charts given here. Based on this, you can do your. Okay, and I think I wanted to also show you all how to do your chi-square manual, but I think it's already time 12:20. So first and last but not least, I like to tell you all certain references from where I got these materials. I developed these materials. You can visit Brandon Ford Statistics and Education. Okay, this particular website for further advanced studies and advanced understanding about all the things which we discussed. Then parametric versus non-parametric statistics by Angela Hebel to 2002. And Andy Field 2009 discovering statistics using SPSS. Okay, I just represented the material and my understanding from the original knowledge or the data source of the above authors. Okay, all the rights are with the original authors itself. I'm just presenting and trying to share my knowledge, understanding of their original contributions. Okay, Jai Hind. I'm open for questions.
Thank you, sir. Thank you for your valuable information, sir. I request the participants, if you have any queries, please let us know about it. If you have any queries pertaining to the session, please put it in the chat box. Sir, there's a question from, one second. There's a question from Nemani Satish. Hello, Balaji sir.
Yes, madam.
Yeah.
Yes, madam.
From Satish. He is asking that even though the sample data is more than 30, can we use t-test?
Okay, can I answer, madam?
Yes, sir. Yes, sir. Over to you.
Okay. Technically, what you're going to do is, if your sample size is more than 30 or more than even until 600, what you're going to do is you're going to use basically your t-test formula only. Until and unless you do not know the population's standard deviation, you're going to use t-test only. Okay, it's not that less than 30 or more than 30. What you're going to do is, I'll just like to show you the, just a minute, from your internet, I like to show you all the t-test for z-test formula. So what happens is, in your z-test, if you do not know the, in the z-test, you're going to use the standard deviation of the population. If you do not know the standard deviation of the population, but still you want to do a parametric study and you have quite a huge sample size, instead of this, if you have collected 600 data, you can use the 600 data standard deviation itself to perform your z-test, and technically what you're doing is the t-test. But what happens is, as I showed you in the table, when the sample size crosses 600, if you do a t-test also, it is as good as doing a t-test. So more the, until and unless you have a strong theoretical populations standard deviation, how much of a sample size you're having, you're going to use only t-test only. It is t-test, but the values are comparable to z-test. That means the margin of error will be very, very less. That's all. So if you do not have the populations standard deviation, whatever you're doing is t-test only. You can use more than 30, more than 40, or until 1000 also, whatever you're doing, you can use t-test only. Thank you.
Yes. Sir, one more question from Som Kanuganti. Can you please explain the margin of error in detail?
Okay. I think there is something I have explained all about a confidence interval. In confidence interval, you can see the sample standard deviation, so sample mean is here and the population mean is here. The distance from this mean to this mean is called as your margin of error. Simply the distance from this mean to this mean is called as a margin of error. Or to put much more in a simpler way, this population mean appears in this sampling distribution at this particular spot. Okay, at this particular spot. So the deviation from year to year is called as margin of error. Okay, so we usually what will happen is, just a minute. So a particular point is nothing but your sample mean plus some distance. This distance from the sample mean to the actual population mean is called as the margin of error. This margin of error is nothing but a standard deviations formula, Z sigma divided by root of n. If you take only this, it is called as margin of error. So point estimate is nothing but average of the sampling mean plus some deviation. This deviation alone, if you consider, it is called as margin of error.
Sir, one more question from, hello?
Tell me, madam.
From same person, sir, Nemani Satish. While calculating margin of error, we are using Z value because to calculate Z, we need population parameters. We don't know about population parameters. Then how to calculate margin of error?
Sir, usually what happens is Z is nothing but it determines upon your confidence level. Here, most of the time, the Z value will be 1.96. Okay, just a minute. I like to show you a particular thing. I think this particular screen is visible. This is a standard normal distributions value at your right tail 2.5% confidence, sorry, at 2.5% level, the value of Z is 1.96. Okay, so right side 2.5%, left side 2.5%, it will come as 1.96. So either you take this 1.96, if you're going for 99%, you take 2.326. If it is you're going to decide what would be the value of Z based on your confidence. For example, if you have more confidence, go for 99% and put this value in the place of Z. If you have less confidence, put this value at the place of Z. If you have medium confidence, you put this value at confidence of Z. Now, how I'm going to determine what would be the value? Literature review. What is your previous studies of what value are they taken? You're going to take that value and put that value in the Z place. So once you put that Z place, take your sample standard deviation and the number, usually 600, divide by 600. So sample standard deviation, you take it 1.96 divided by 600, you'll be getting your margin of error. Yes, ma'am.
Yeah. Sir, one more question from Manoj Hatia. Please tell, if sample size is 30, then will it be considered as a small or a large sample?
Okay. If the sample size is 30, it is of course considered as a small sample only. It is not considered as a large sample, but usually what happens is if your entire theoretical population itself is very low, that time your sample size of 30 might be quite large or less. For example, if you take the number of telecom operating companies in India, if you take like that, or the number of cable TV service providers in Bangalore, it will run only in 100 or 200. At that time, if you take 30, it's a quite huge sample. Okay, so based upon your theoretical population, 30 can be either a small size or a large size. But let us assume you're taking into consideration quite a huge theoretical population, like salaried people in Bangalore, middle class people in Bangalore. If you take like that, then 30 is quite low and nobody is going to accept it. One thing, this 30 can be used for your pilot study purposes, but not for your actual purposes. That's why it is called a student t-test. What during those days researchers used to do is, as soon as they try the question, it is not a foolproof method. They try a questionnaire, they'll go to their classes, and in the classes, they'll ask the students to think them as the potential respondent, and just a minute. They think as a potential respondent and they are going to answer on behalf of the potential respondents. They're going to answer on behalf of the potential respondents. So here, based on the students' response, they're going to come to an analysis of whether to validate the questionnaire or not. This is called a student t-test. So for pilot study purposes, pre-test purposes, you can use your t-distribution. Otherwise, do not use your t-distribution less than 30. You should always go for 600 only. Thank you.
Sir, one more question from Somu Kanugati. How to understand the concept of degrees of freedom? Suggest some books.
I think a degree of freedom is actually a very quite a simple tool only. to understand. I can just easily, I can try to explain you all. Okay, so let us imagine you're having a box with 3 compartments and you're having 5 objects, a ball, a bat, then let us assume ball, bat, then you have an pen, then you have an rubber, then you have an sharpener. Okay, so you have ball, bat, then you have a pen, you have a rubber, then you have a sharpener. So let us say you're having 3 places. So in 3 places, what happens in this 3 place? The first compartment, in how many ways you can fill? 1, 2, 3, 4, 5. You can fill either bat, ball, pen, rubber, or sharpener. So I have 5 options to fill this one. So here in the first box, my degree of freedom is 5. So you think I put a ball here. In the second, I have only 4. You think I have bat here. At the last, I do not have any freedom. Okay, I have 3. At the last, I have again still 3 options left. This is you think I put your pen. Okay, so this is called as your degree of freedom. So degree of freedom is how much liberty you can take while you're calculating, you're trying to calculate your estimates. That is called as your degree of freedom. In order to better understand your regarding your basic statistics, all those kind of things, I can share you certain books, but basically I think Andy Field's basics of SPSS will, discrete statistics using SPSS by Andy Field will do a good justice regarding that. Thank you.
Okay, sir. The last question from Ishwar Gowda. Is there any limit for sample survey?
Okay. As see, the best kind of analysis which you can do is your percentage analysis from a census survey. If you are collecting from census, what happens is you're going to consider all the entire theoretical population, take their parameters and describe the data. Okay, so that is the best particular kind of statistical analysis you can do. For example, you take in India, they do census, and based on census, they give you all the average, average Indian literacy, average gender ratio, all those kind of things. So basically in your statistics, we say something called as descriptive statistics. It describes the data. Okay, that this is the data, this is its central tendency. From the central tendency is deviating so and so. That's what we studied in your BCom and MCom and all. Okay, that is the best possible thing. But here what we're doing is we are doing something called inferential statistics. From the sample, we're trying to find how the original population will be. So of course there will be a marginal of error. Okay, that's what we studied in confidence interval. We cannot have 100% confidence. That is the major disadvantage of sample surveys. Thank you.
Okay, sir. Thank you so much, sir, for a wonderful session. You have enlightened us regarding the inferential statistics and many more things about Z-test and T-test. Thank you so much, sir. Like you started with probability study and then you took us to different words, different extreme. Thank you so much for your wonderful session. Now I request Shri Manjunath BN sir to deliver the vote of thanks for the respective dignitaries. Manjunath sir. Over to you, Manjunath sir.
Yes, madam. Very good afternoon to all the participants, respected principal, organizers present here. It's my pleasure to propose vote of thanks on this occasion. First of all, I would like to thank our principal, Professor M. Shivana sir, Government Freshers College, Toribiddur, on behalf of all the participants, thank you very much, sir. I would like to express my sincere thanks to our today's resource person, Lieutenant Balaji A, for an excellent presentation and making this seminar very meaningful and interesting. Thank you very much, sir, on behalf of the entire institution and all the participants. I would like to express my sincere thanks to the program coordinators, Dr. Matsudan Reddy sir, Dr. Zebula sir, and IQAC coordinator, Dr. B.R. Gangadhar sir. Thank you very much for your valuable efforts. I would like to present my sincere thanks to all my beloved colleagues, Akshata madam, Parvatama madam, and Suresh Prabhu sir, for your active involvement in this seminar to conduct effectively. I would like to extend my sincere thanks to all the participants present here. Thank you very much. I am very grateful for this opportunity. Over to Akshata madam.
Thank you so much, sir. Now, I request all the participants to fill in the feedback form, which is posted right now. So please fill in the feedback form, and which will not be posted in any WhatsApp group. Please fill in the feedback form, which is given in the chat box, and it is even put in the YouTube live chat. Please use that and fill in the feedback form. And before that, I request you all to turn on your videos, sir. Balaji sir, please stop sharing.
Yes, madam.
Please stop sharing, sir. Stop sharing the screen. Yes. I request all the participants to turn on your videos for a snap. Balaji sir, if you don't mind, can you please turn on your video?
Yes, madam.
Just a second, madam.
Yes, sir.
Right. Done, madam.
Yes, sir. Thank you, sir. Thank you, Balaji, sir. Thank you so much for being being with us for today's session. Thank you so much, sir. And I request all the participants to fill in your feedback form. Please fill in your feedback form. And tomorrow for the day 6, we all meet again at 10:50 a.m. Please fill in the feedback form using the link given in the chat box, and it will not be posted again in the WhatsApp group.
Thank you, Balaji sir. This is Gangadhar, IQAC coordinator. Thank you so much, sir.
Thank you, sir.
Thank
Thanks
you.
a lot, sir.